All right, so in chapter 4, it's all going to be about eigenvalues and eigenvectors and some applications of those. Okay, we use those a lot in differential equations. If you've not been in that class yet, you use them in some electrical stuff as well. Kind of in the same kind of vein of thought. So the interesting thing is this: if A is an n by n vector, or a matrix rather, then a scalar lambda, which is what we use, one of the eigenvalue of A. So so lambda is an eigenvalue of A, is a non-zero, if there is a non-zero vector x such that ax equals lambda x. Okay? Such a vector x is called an eigenvector of A, and more specifically, it is the one that is associated with lambda. Now I'm going to go ahead and put a little lambda sub 1 right there, lambda sub 1, x sub 1, x sub 1, x sub 1, and then therefore this guy that corresponds with this guy. Pretty much in every problem that we deal with, there's going to be multiple eigenvalues. Frequently they'll be different. Sometimes they'll be repeated eigenvalues. But to keep them straight, we're going to label them as lambda 1, lambda 2, lambda 3, and so forth. And then, of course, we'll have x1 and x2. A is just A. A is the same matrix. But there are multiple eigenvalues with a vector. In the case of an n by n, there should be n eigenvalues. Does that mean that they will be different? No, it could be repeated. But very similar to when you're actually when you're doing polynomials. If you have x squared plus 2x plus 3 or something, you're going to have two roots, right? Do they have to be the same? No. Could they be? Sure. Can they both be real? Yeah. Can they both be imaginary? Yeah. Could they be one of each? No. Not in this case, because you always have to have group, you always have to have, two imaginary roots or pairs of multiple roots. In actuality, this right here is going to be a big deal because that is how we're going to end up finding those eigenvalues. Okay, and we're going to talk about that in a little bit. So when we go about finding them, if someone said to you, "Hey, is this true?" You can plug it in and you're like, "Hey, that works. That's great. That's neato. Whatever." Okay, so the idea I mean by that is this. So, for instance, I'm going to pause you in a second here. I'm going to set one up, and then I'm going to go away, and I'll come right back to you in a minute. If this is our matrix A, okay, I'm going to pause and come back momentarily. All right, so I have this matrix A. It happens to have eigenvalues of 7 and 2, and it happens to have eigenvectors of 1, 1, and 1.5, comma negative 1. To show that's true, this is what we need to look at. So to see that these are, in fact, the deals, look what's happening. So if I take this times the vector 1, 1, it is equivalent to taking 7 times 1, 1. In other words, I better get 7 and 7 when I multiply this out. Well, I'm going to get 4 plus 3 is 7. Yep. 2 plus 5. No way. Yep. Way, dude. Way. So that shows. Now, the other one that'll work for is if you have 1.5 and negative 1. That better equal 3, negative 2. And that's going to be 6 minus 3 is 3. And it's going to be 3 minus 5 is negative 2. No way. But that's the only number that will work is 7 and 2. If you use 2, you must use this eigenvector. If you try it with 1 and 1, it won't work. You like, what about the number 3? Can you do it with 3? No, 3 will not work, sir. The only 2 that it works for are 7 and 2 for this matrix. For other matrices, it'll be a different story. Okay? That is a big deal. So if a person were to ask you, hey, can you confirm it? Well, yes, I can. And how would I confirm it? It would make that statement a true statement. Okay? So in other words, this eigenvector value times its vector is the same as taking this A matrix times the eigenvector itself. Okay? Now, where did I use that? Well, we'll get to that later on, friend. That's just how that works. Now, so here's another one here. So if A is our n by n matrix again, and lambda is an eigenvalue, okay, the collection of all eigenvectors together with the 0 vector is the eigenspace. Okay, so the collection of all eigenvectors corresponding to lambda together with the 0 vector is called the eigenspace of lambda. And it's denoted by this. Okay, so that's just something to think about there. So when we do that, oh, and by the way, come back over here. Just want to mention one thing before I get too carried away. Like, Jay, could I have done this with, would 2 have worked here? Yes, because you would end up with 14 and 14 and 14 and 14. And so what you're going to see is that 1 times any constant will work, and some other constant, we'll call this one K1, times this guy would also work. Again, very similar to the idea of when you did elimination, or when you get the idea of getting common denominators. They're just multiples is all they are. Okay, so just be aware of that. This is how that kind of goes there. All right. Now, someone might rightly ask, Jay, how do you go about finding an eigenvector? I'm glad you asked. So, in the case of our first A matrix, which was 4, 3, 2, 5, we're going to take that guy right there, and we're going to subtract from it our lambda times our identity matrix. So in this case, since it's a 3 by 3, we'll be subtracting our lambda times the matrix 1, 1, 0, 0, 1. Take lambda times that, of course, it's going to appear here and here. And so what's going to end up happening is, or I'm sorry, so if it was a 3 by 3, it would be. This is a 2 by 2. I was looking at the next one. Sorry. There we go. And so what's going to end up happening, well, we're going to take lambda, or A rather, so it's 4, 3, 2, 5. And let's subtract 7 times this guy, which of course would be 4 minus 7 and 3, 2 and 5 minus 7. Okay. So when you do this, what do you end up with? Well, you end up with negative 3, 3, and you end up with 2, negative 2. And what we're going to do with that, guys, we're going to multiply it by some A and B so that we get 0 and 0. That is how this is solved. Now, That's how most books approach it. That's kind of how I like to think of it. But when you see this equation right here, this is the exact same thing as saying this. And it's the exact same thing as saying this. That's a B, stupid. Which, of course, you could then solve by method of using a augmented matrix, which is how your book shows it. Nothing wrong with either one. What do you do, Jay? Well, I know. That's what I'm going to do. I am going to, well, first of all, I think, well, yeah, I think I will. I'm just going to divide the top one by 3 just for a good time. I'm going to divide the bottom one by 2 just for a good time, just because I can. I don't have to. I can wait till later. I need to get a 0 here, yeah? Let's do that. 1, 1. Oh, I know. So let's just take row 1 plus row 2. And you're going to get what does this mean? It means that there are infinite numbers of solutions for these guys. Well, what do you mean by that? Well, what I'm saying is, just previously I said you could have taken 1, 1, or you could take 2, 2, 3, 3, 5, 5, 2.5, 2.5, whatever. As long as they are 1, it's a 1-to-1 relationship is what we're saying. Okay? So what this is tantamount to saying is that negative A plus B has to equal 0. In other words, B has to equal A. Well, if I choose A to be 1, then B, of course, follows to be 1. But if I choose A to be 3, then B is 3. But you see it's a 1-to-1 correlation. That's how that works. Okay? That will always be true for every single eigenvector that is a unique eigenvector. Okay? Sometimes later on when we have repeated eigenvectors, so like eigenvalues, you have like 2 and then 2 is like a double root, if you will. That's a little different. Okay, we'll cross that bridge when we get there. Okay, and so keep that in mind as we go along. It's going to be kind of funny-ish, sort of ish, and so we'll kind of play that by ear. Okay, cool. So we will be doing some examples like this guy. Cool. We are going to also go about finding eigenvalues. So in my mind, we're going to do, you're going to use 4.1 and 4.2 and 4.3. Where's 4.3 at? So I've already kind of showed you how to find determinants. Okay, that's just kind of how I go about it. So 4.2, I'm going to kind of breeze through that quickly. I don't really need to fool with that. The way that this book approaches it is they teach determinants when they get around to finding eigenvalues, which is cool because that's how you have to do it. However, I see the point in teaching determinants earlier, and so we'll hit them again. And so then I probably wouldn't teach them in this section if I was writing a book, but no one asked me, and I don't have a PhD, so that's how life goes. So again, I'm going to do 4.1, 4.2, and 4.3 kind of all in one fell swoop. And because I think they all, in my mind, go together. There's really no way to get around that. 4.4 we'll leave for later because it's more of the same. It's a little extra. So suppose I have an A matrix. I'm going to pause just a moment to make sure this one comes out nicely. So I beg your pardon. Okay, this one should work nicely. So this is my A matrix. Now, Jay, how do we go about finding this? Glad you asked. So what we're going to do is we're going to take our A matrix minus, and we're going to write it just like this. And you're like, well, yeah, that's cool. What does that mean? Well, it means you're going to end up with this every time. In essence, you're just going to throw the 3 minus lambdas behind there. Okay. Well, then what do I do, Jay? Well, then we're going to find the determinant. We're going to find the determinant of A minus lambda I. And whatever that is, we're going to set it equal to 0, and we're going to solve for lambda. Now, when we do this, you will always be getting a polynomial. Polynomial, so x cubed, x squared, x to the 19th, whatever it happens to be. So a polynomial, of course, if it was x to the nth power, will have n roots. This is why we will end up having lambda to the n, so we'll end up having lambda, we'll have an n of n number of lambdas. Okay, and so just kind of keep that in mind as we go along. The determinant here, remember, it's you cross multiply, so this one times this one. Minus this one times this one. And again, this is in the case of a 2 by 2 matrix. Equals 0. By the way, this polynomial, check it out. It's called the characteristic equation. Okay. And so here we go. If you distribute this out, a little foliage, you get lambda squared minus 5 lambda plus 6 minus 12 equals a goose egg. Hey, that factors. Yeah, the early ones do. Do they all? No, they do not. Does that make them more fun? I think so, sure. So our lambdas here are 6 and -1. Those are our two lambdas. You're like, oh, well, that's it? Yeah, that's it. Well, then how do I then go about finding my eigenvalues, or eigenvectors rather? Well, once again, you replace the lambda here and here with one of the eigenvalues one at a time. So 2 minus 6, 4, 3, 3 minus 6. Jay, is it always going to be like this? Yeah, always, friend. And so you're going to get -4, 4, 3, -3. And you're like, wait, I've seen this problem before. I know you have. So in essence, remember what we're saying is that this times a and b equals 0 and 0. In essence, you're saying -4a plus 4b equals 0 and 3a minus 3b equals 0. What values of a and b make that true? Okay, well again, it's pretty obvious in this case. It's not always as obvious as others, but this one's not hard. Again, it's very easy to do. You can do this if you'd like. Oops. And you'll get, of course, this, oh, no. This, and this. And when you add them, you'll end up with this, and as always promised, zeros on one of them. Because, again, the idea is there is an infinite number of ways to pull this off. In other words, -a plus b has to be 0. Or in other words, b equals a. So once again, for this particular problem, we will see that we have a vector of 1, 1. That will not always be true. Frequently, it will be something different. Now, if you put in a -1, now be careful. A lot of people will screw this up. It's 2 minus a -1, so 3. And then down the bottom, you're going to have, well, you have 3, and then 3 minus a -1 is 4. Well, now, no way. Weird. So if I were to do this, row 1 minus row 2, well, I will end up with, unsurprisingly, this. Now you're like, wait. These are different. It's not, you couldn't divide. Well, I know exactly. So in other words, 3a plus 4b is equal to 0. In other words, b is equal to -3/4 of what a is. Or, if you're weird, friend, you do it your way. Okay? Now, what does that mean? Well, I don't know. What do you think that means? So when you do this problem, you can do it a couple of different ways. Okay, I don't care. I personally like this one. Okay, so it doesn't make any difference to me. So you could, for instance, let a equal 1. All right. Well, if a is 1, then b is -3/4, right? That's fine. It's gross, but it's fine. If you let a equal 4, then b is equal to -3, correct? In other words, it would be what would make them equal over here. Does that make sense? So you could do this, 4 to -3. You could do 1 to -3/4. The ratio is the same. Okay, so it makes no difference how you go about it. One of those guys, I will probably use this one. You're certainly welcome to use decimals. That's fine. But it's nice to have a little more of a cleaned up version of it. Okay. We'll do more. We'll do more. Let's do another 2 by 2 here because they're fun. Now, Jay, when you go about doing this, how do you go about finding ones that work nicely? Normally, I just don't guess. Although I'll be honest with you, the first one I did today, I just totally made that up and I didn't check myself or anything, and it worked, and it was weird. check this out. So I know that this is going to be 6 minus lambda and 7 minus lambda. So when I'm making up a problem at home, you can play teacher here with me. I am going to FOIL this mess out. It's going to be lambda squared minus 13 lambda plus 42. Now you're like, wait a minute. If I was going to get 13 to factor, right? In other words, not 13 to factor. I would need what adds up to 13. Well, 8 and 5 add up to 13. Am I right? What are 8 and 5 the factors of? Well, 8 and 5 are the factors of 40, right? And they need to both be negative. In other words, I'm doing this in my head. I'm going, well, wait now. Lambda minus 8, for instance, and lambda minus 5, for instance, would make this 13. You with me? But that means I'd have to have positive 40 when I multiply the outside. Well, I've got 42. That means I got to get rid of 2. Oh, that's easy. Boom. Minus 2. Minus 2. See that? And so when I'm setting these problems up, that's how I go about setting them up for you. Okay? I typically, sometimes I just make them ugly. Deal with it, friend. But so if this is my A, and again, this is how I'm setting it up. So then I'm to go find my lambdas, I'm going to do this. And I'm going to find the determinant. So just 6 minus lambda, times 7 minus lambda, minus 2. So that's going to be lambda squared minus 13 lambda plus 40 equals 0. So lambda minus 8, lambda minus 5. So my lambdas are 8 and 5. By the way, there is no rhyme or reason to which one is lambda 1 and lambda 2 in my mind. I just put them. There is no right or wrong way to do that. Bear in mind that later on in the text, after I don't know, there'll be a part of the test where it's, well, I don't know, we'll see how it plays out. There are computer programs, of course, that can find these, and of course your calculators can find them too. However, don't even think about turning in the goofy answer that the calculator gives you for this, because you have to understand and read it, and I'm not going to tell you how until later in the term. So I want you to practice doing it the hard way, and on the test you'll have to do it the hard way. Okay, later on, maybe there's one problem on the test where I'll allow you to use the calculator for that, but we'll talk more about that later on. But the point is that they will list them in order, so you need to remember this one goes with this particular vector. Okay, so if you plug your 8 into there, 6 minus 8 is negative 2, and then 1, and then 2, and then 7 minus 8 is negative 1. Okay, to solve this, what are we going to do? Well, it's R1 plus R2. So you end up with negative 2, 1, 0, 0, 0, 0, as always. So negative 2a plus b is a goose egg, so b is equal to 2a. Well, if I let a equal 1, b is equal to 2. Ta-da! Now, if I were to plug this fella in, I'm going to get 1, 1, 2, 2. 1, 1, 2, 2. Well, that's going to be 2r1 minus r2, I guess, right? So that's going to give me 1, 1, 0, 0, 0, 0. Don't fall prey to this. A lot of people go, oh, 1, 1, it's 1. Wrong. So A is the opposite of B. Well, what is A? I don't know. Let's just say A is 1. Well, if A is 1, then B is negative 1. Well, Jay, the book had that. I had negative 1, 1. Good for you. They're the same dimensions. They're, I say 5 and 5, but one's positive and one's negative. Ta-da! Yay, you did it right. Woohoo! Are you sure? Literally, I'm positive. Literally, I'm positive. Okay. Let's do another one here. One moment, please, while I get it. Okay, so here's an example of an A matrix. It's a 3 by 3. This is the most I'll ever make anyone do by hand, I think. That's just kind of ludicrous. I mean, you could, of course, make people, if you were a horrible person, make them do a 4 by 4 by hand. I think you would find that a lot of the ones that the book gives you, maybe I'll do a 4 by 4 for you to demonstrate that. The thing to remember with that is that the book gives you a lot of zeros frequently, and so it makes your life easier. So to do this, we're just going to go minus lambda, minus lambda, minus lambda. So recall that to find the expansion by minors, it's 1 minus lambda times this little determinant. So this little fella right here. And so it's 0 minus lambda, which of course is negative lambda. It's always minus the next one over, so minus 1 times, and it's 1, 1, 0, 1 minus lambda. And then it's going to be plus, and then it's going to be 0 times, and I'll go ahead and show it, even though we're not going to do it. Okay, so if I do this problem out, okay, first things first, of course, inside this piece here just cancels off. That's handy. Here, you're going to get 1 minus lambda times negative 1. So you're going to get lambda plus minus 1 here. Here you're going to get negative lambda squared. Actually, you're going to get lambda squared. I lied to you. Lambda squared minus lambda. And you get minus 1. That's coming out of the middle. And then you're going to have 1 minus lambda. With a 3 by 3, one would expect that one would get 3 eigenvectors. And that's exactly what's going to happen here. It's because you're going to get lambda cubed here. So you get negative lambda cubed. You get plus lambda squared. You get plus lambda. And then you're going to get minus lambda squared plus lambda minus 1. So that's negative lambda cubed. These guys go away. These guys... No, these two guys add up to another lambda. So plus 2 lambdas. Minus 1 plus lambda minus 1 equals 0. So you're going to get negative lambda cubed plus 3 lambda minus 2 equals 0. How do I solve that, Jay? Well, there's a variety of ways. Say you're a Desmos person like myself. Love me some Desmos. Cool. You can do it that way if you like. I'll do it a couple ways. I don't know. I'm a sucker for a little bit of algebra. It's a good time. You know it, man. So negative lambda cubed plus, what did I say? Plus 3 lambda. Plus 2. Minus 2, sorry. Minus 2. There you go, friends. Boom. And boom. Cool. Now, what does that tell us? Well, if you remember, if it's on the line, that tells us that it's what? That tells us that we have ourselves a double root there. Are you with me? So what that means is this factors is lambda plus 2 and lambda minus 1 twice. This isn't quite accurate because what you'll see is if you graph that, it's kind of bass-ackwards and upside down. Lambda minus 1, lambda minus 1. Let's say that one was lambda plus 2. And you forgot your parentheses, dopey. Oh, it's like a mirror image, Jay. That's right. So I'll put a negative in front of that guy. That's true. Oh, that's hot. And of course, what most people would do at that point is actually make this guy there you go. See that? But the idea is still the same. Okay. Now, what that means is how does that look like? Well, if you come into here, into our matrix back up here, okay, we solve this equation. There they are. And so now we have lambda equals, we said equals 2, negative 1, or negative 2, positive 1, and positive 1. So we say we have a multiplicity of 2 here. In other words, it's a double root. Okay. Another way to do it on your calculator, of course, is to go yes, cool. Then you can go solve. Actually, you can go solve. Stop it. Solve. There you go. And you can say negative x cubed minus or plus 3x minus 2 equals 0, x. And if that makes you happy, go for it. Just bear in mind that when it's a double root like this, you don't know which one is the double. If that makes sense. That's why I like to graph a little nicer, but whatever. Okay. Now, because this is a double root and it's going to be a little different, so I'm going to show you how that works in a few minutes. Let's start with the -2 one though for fun. If you put the -2 one in, you're going to get 3, 1, 0. You're going to get 1, 2, 1. And on the bottom row, you're going to get 0, 1, 3. So if we were to augment this, let's see what happens, shall we? So if one were to do this, like, all right, let's do this. Let's do a little R1 minus 3R2, I guess. Why not? And so you're going to get 3, 1, 0, 0. And then you're going to get, well, 0. You're going to get R1 minus 6. So 1 minus 6 is -5. And you're going to get -3. And, of course, 0. And then this, 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 and this. You're like, all right, box office. All right, now what happens? Well, feel like you can do 5R1 plus R2 and 5R3 plus R2. And that will give you 15, 0, -3. And then it'll give you, ouch. This one didn't change. And then 0, 0, and then 15 minus 12. One moment, please. All right, so where do we leave off? Oh, we're here, yes? So clearly this bottom one can be made into 1. By dividing, of course, and then you could just take 3R3 plus R1 and 3R3 plus R2, and you will get and you will get this, this, and this. Okay, what does that mean for me? Okay. Wait, like, wait, couldn't these be 1s? Yeah, they can. I'm a little discombobulated. I had to answer the telephone. That kind of threw me off here. Something's a little screwy. I'm going to double check this for a sec. Hang on a sec. Okay, I made a little boo-boo here, apparently. When I did my multiplications out, I didn't. This isn't correct right here. So it's this piece right here is what it should have come out to be. Okay. So let's go ahead and graph that on the old Desmos, I guess. So -x cubed. Jay, why can't you let's use a calculator? I will, but not at the first part of this. Plus 2 lambda squared. Oops. What just happened? Plus 2 lambda squared. Plus lambda minus 2. Oh, that's hot. -1, 1, and 2. There's our answers, friends. Okay. So -1, 1, and 2. Good night, nurse. So our lambdas. 1, -1, and 2. Okay. There's what we're starting off with. Okay. So if you come back in and you put in your values. Holy mackerel. If you put in 1, you're going to get 0, 1, 0. And by the way, you realize why I was wrong, right? Because I was putting a value and I got something other than a 0, 0, 0 row. That's not going to happen. So you get 1, -1, 1. And you're going to get 0, 1, 0. This is hot, friends, because as one can see, well, the first thing one ought to do is put this one other row on the top. But other than that, shoot, one is done because these two rows are clearly the same. And because they're the same, if one would just add them together, you're like, oh, this is easy. Boom, 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 done. So what you see is you're going to have the 1, -1, 1, 0. These two rows are zeros, meaning you have a nullity, if you will. That's a two-dimensional nullity, right? Ooh, that's cute. But more importantly here, what that's saying is that A minus B plus C has to equal 0. Like, what on earth could it be, Jay? Well, I think if you did 1, 2, 1, that would work. Well, how do you know that? Well, I feel like 1 plus 1 is 2, minus 2 is 0. Yay! And that is for lambda equal 1. Okay? And so there it is. Now, what happens with -1? Well, if you put -1 in, you're going to get 2, 1, 0. And then you're going to get -1 is going to give you 1, 1, 1. And we're putting in 1, right? Right. 1 is, no, we're putting -1 in, right? -1. 0, 1, 2. Nice. Okay, I like it the way it is. We'll do R1 minus 2 R2s, I guess, just for fun. Give me 2, 1, 0, 0. That's going to give me 0, and then -1, and then -2. Wait, -2. That's nice. And then 0, 1, 2. No way. Now, if you add R1, 2 plus R3, you get dun da da da. So what does that say? It says that 2A plus B is a goose egg. What about C, Jay? It doesn't matter what C is. Does it have to be 0? In fact, friends, you wouldn't want it to be 0, probably. Well, you could make it 0 if you wanted to, but it doesn't make any difference here. So, check it out. When I do this problem here, what am I going to get? Well, I'm going to get, well, I feel like the 2A is equal to, well, -2A is equal to B. What are you saying? Well, I said, well, let's say A equal 1. Well, that means B is equal to -2. Well, what about C, Jay? What about it? Let's find out, friends. What about it? So let's do this. 1, 1, 0, 1, 1, 0. 1, 1, 0. Remember, we know what's supposed to happen here. 0, 1, 0, 1. No, I'm getting dizzy. 1, 0, 1. Whee! 0, 1, 1. Times our eigenvector. Now our eigenvector is 1, -2, something. And we know that that has to equal, now what was our eigenvalue this time? Well, our eigenvalue was -1. So -1 times 1, -2, something. Okay? Well, what on earth could that something be? Let's find out, shall we? So that's 1 times 1 is 1. 1 times -2 is what's -2. So then, excuse me here. Let's put a C in here just for fun, shall we? So it's going to be 1 minus 2 plus C. Nice. Nice. Now, what does that need to equal? Well, it needs to equal -1. Yes? That's the top row over here. And you're like, well, wait a minute. Wait, I feel like, wait, this is -1 plus something is equal to that. Well, it looks like C should be 0. You're right, pal. Now check this one out. Look what happens here. So you're going to get, if I didn't screw this up, it's going to be 1, 0, 0. Right. So if you do this, you're going to get, hold up just a sec, something's a little screwy. Except my algebra is a little off here. Weirding me out. Okay, so let's finish. My algebra wasn't wrong, it was just weirding me out. So I have, check this out, so I have 1 times 1 plus negative 2 times 1, right? Plus 0 times c equals negative 1. Now, that was my problem right there. Are you with me? Because the c went away, and that's my biggest issue. I'm not a very good mathematician some days. 1 times 1 plus 0 times negative 2 plus c has to equal 2. Are you with me? Okay, so you look at that, you're like, oh, okay, well, that's interesting. So then let's keep going. So then, well, what happens next? We're going to have 0 times 1 is 0 plus negative 2 times 1 plus 1 times c is equal to c. Are you with me? And so negative c rather. So if I check this out, let's see what happens here. Well, this is going to be, this is 0. This is negative 2 plus c equals negative c. So in other words, 2c is equal to 2, which means c equals 1. Okay. This one here doesn't make any difference because c was, times by 0. This case here, you get 1 plus something equals 2. C equals 1. Are you with me? So c needs to be this. So there is, you see, our eigenvector. So the eigenvector associated with negative 1 is 1, negative 2, 1. Now let's do the last one. The last one, of course, is we had an eigenvalue of 2. I'm just going to copy that. I'm tired of scrolling. Paste. Cool. Oops, minus lambda, sorry. That's what I wanted to do. Now, if you plug in 2, you're going to get negative 1, 1, 0. You're going to get 1, negative 2, 1, and you're going to get 0, 1, negative 1. Nice. Little row 1 plus row 2 action. Oops, sorry, got to augment it. This plus this is negative 1. This plus this is 1, 0, 0, 1, negative 1. Nice. And you end up with this. Like, oh, cool, great. So you go, all right, so negative a plus b is equal to 0. That's hot. What does that mean? Well, it means that b is equal to a. Cool. But what about c, Jay? Well, what about it, sir? What about it, sir, ma'am? Because if I do this, what I'm saying is this. I have then negative 1. Well, I'm saying we have a. So it's going to be a, remember, is 1, 1, 0, 1, 0, 1, 0, 1, 1 times. Now we said that A and B are equal to one another. Okay, well if that's true, then I'm going to pick them to be 1 and 1 just because I feel like I can. And then remember we were dealing with this with 2. And so if I do this, it's 1 times 1 is 1, or 1 times 1 is 1 plus 0. Get 2 equals 2, so duh on the top row. That's not helpful. The next row down is very helpful. So it's 1 plus 0 plus c. So 1 plus c is equal to 2. C is equal to 2 rather. That's cool. And then in the bottom row, you're going to have 0 plus 1 plus c is equal to 2c. So if you do this, you get c equal 1. And then this, of course, is the same, c equal 1. So c has to be 1. And so that should be our eigenvector that's associated with that guy. Okay? I'll tell you another one here. I'm going to find the other one. It's nice. Nice-ish, kind of. All right, I'm back. Here's one. Let's go ahead and do this one just for fun. Okay. So again, expansion by minors. And then you take 1 minus lambda, 2, 2, 5 minus lambda. Minus 4 rather, always minus, so minus a minus 4, so plus 4 then. And then negative 2, 2, 4, 5 minus lambda. Minus, so it's plus, but it's negative 2, so plus negative 2, so negative 2, 1 minus lambda, 4 and 2. So if I do this, this times this, I'm going to go ahead and write it out. Oops. And so if you do this out, you're going to get 1 minus lambda times 5 minus lambda minus 4 plus 4 times, and then it's going to be negative 2 times 5 minus lambda minus 8 minus 2 times, and that's going to be negative 4 minus 4 times 1 minus lambda. So here you're going to get negative 2 minus lambda, and then you're going to get lambda squared minus 6 lambda plus 5 minus 4 minus, or plus 4 rather, and then it's going to be negative 10 plus 2 lambda minus 8. And then you're going to get negative 2, and then you're going to get, this is negative 4, so it's going to be negative 8, and then it's going to be plus 4 lambda. Goodness, what a mess. I need an easy win over here. I'm going to do this first. So it's going to be minus 8 lambda plus 16. So negative 18 times 4 is negative 72. 8 lambda. And then you're going to get, I don't know, let's do this. It's going to be negative lambda cubed plus 6 lambda squared minus 5 lambda plus 4. Oh, fart. Oh, I see why. Never mind. Hang on, never mind. 5 minus 4 is 1. Are you with me? So then it's just going to be minus lambda. There we go. I almost screwed that up. And then you're going to have negative 2 times that, so negative 2 lambda squared, and then you're going to have plus 12 lambda, and then you have minus 2. So when it's all said and done, you get negative lambda cubed, and then plus 4 lambda square plus 11 lambda minus 2 plus 8 lambda minus 72 minus 8 lambda plus 16. These guys cancel out. Negative lambda cubed plus 4 lambda squared. Here you get 11 lambdas, and you have 74 minus 16 is what? 58, I guess. Negative 58 equals 0. Well, the truth will be, if the proof will be in the pudding here. See if I screwed this up. So solve negative x cubed plus 4x squared plus 11x minus 58, oops, equals 0. Solve for x. One moment, please. Unbelievable. By the way, let me just finish this off. I am in a real function mode right now currently. And so when I hit solve, it only gave me the real values of this function. What a guy can do is put in csolve. And in fact, there's real and complex roots to this guy. There they are. Okay. We'll get into that later on, and the ones I give you will not be that disgusting. That said, suffice to say, I made a little boo-boo right here. That should have been positive 2. Should be minus 16 plus 8 lambda. So I'm going to have now 16 lambdas more than I currently have. 27 lambdas, I guess. And then I have another negative 16 from this, so negative 42 looks like, maybe. No, because it was positive 16. Now it's negative 16, so it's actually 32 less than I had. So minus 16 more. Oh, well, here, I'll just tell you what it is. Oh, it should have been plus. It should have been minus 90. Oh, okay, so I should have just got it away. Anyway, there it is. Now, then if you solve that guy, what you will find is it's going to work this time. So don't fret. I am not going to make this hard on you. I will make it to where you can use the calculator. In fact, I'll probably show you that later in this video. I'll probably make another video for it. But there they are. So 6, 3, and negative 5. Lambda equals 6, 3, or negative 5. Okay. No one's going to do more than a 2 by 2 by hand. I'm just demonstrating how this works. That's all I'm doing. Okay, so if our original equation up here, our original guy is this. Oh, shoot. Darn it. Oh, you hippie. Good night, nurse. All right, here we are. So, if you were to plug this in, paste, you end up with this. Okay, let's do 6. Then I'll show you how the computer figures them out here for us. So if you put in 6, you're going to get negative 8, negative 4, and positive 2. You're going to get negative 2, negative 5, and 2. And you're going to get 4, 2, negative 1. Oops. If you augment this, oh, I don't know. What are we going to have? R1 minus 4R2 and R1 minus 2R3. So if you do this, you're going to get 0. And you're going to have negative 4 plus 20 is 16. And you're going to have 2 minus 8 is negative 6. Then you're going to have 0, obviously. That needs to be plus, though, doesn't it? Yep. And then it's going to be negative 4 plus 4 is 0. Is that right? Well. And then you're going to have 0 minus, you're going to have 2 plus negative 2 is 0. Well, that's hot. Cool. Nice. Cool. Awesome. So what does that say to me? Okay, well, it says to me that the following things must be true. Now, could I go a little further with this? Yes. Would I suggest that I do that? Yes. I would take 4 R1 plus R2, which will give me negative 32, 0, 8 plus negative 2 is 2. Isn't that right? 8 minus 6 is 2. Yep. And then this, and this, and this, and this. Nice. So it's not as easy as it looks. You're like, oh, okay, well, I'm basically done. You are basically done. I would take it this next step further if it was me. That's all I'm saying. 8, negative 3. Okay, so what that's saying to me is this, is that negative 16 times A is equal to C, and 8 times B is equal to negative 3C. Okay, now, it doesn't matter how you go about this problem. It's going to be kind of gross unless you really put a lot of thought into it. Okay, so if it's me, I'm going to put something, I'm going to use the number 48 because 3, 16, and 8 all go into 48. I think that's kind of how I'm going to play that out. I'm going to let C equal 16. I'll let C equal 16. If C is equal to 16, that means A is equal to negative 1. And then B is equal to, now that would make it 48, so B would equal 6. Is that correct? Negative 6. I believe that is correct. So negative 1, negative 6, positive 16. Okay. Now that is, a way to do it. Of course, you're like, oh, it's kind of neat. It is. Now, what I would also consider you think about is the following: Now I'm going to put that in as a row vector just because it's easier, but it doesn't matter, I guess. I can actually do a transpose. What I want you to see is, just be aware, okay, so what I could do is I could take and divide that by 16, for instance. You're like, okay, well, yeah, those are decimals. Oops, oh, darn. And so I could grab this and make them into decimals. You're like, well, that's, yeah, okay, cool, that's nice. And I would recognize those decimals if I saw them. That's true, I would. What if I looked at that as a vector, though? And I said, listen, this vector, 1, -6, 16, has a length. And I said, well, what is the, and let's just call this vector, let's call this x1, I guess. What is the magnitude of x1? Okay, well, the magnitude of x1 is simply what? Well, it's it is what it is. It is the square root of 1 plus 36 plus 256, I guess, yes? And so the square root of, so let's take this guy here and let's divide him by his magnitude, which is 1 plus 16, no, 36 rather, plus 256. You get that nasty mess, which I can then just hit diamond enter, and I get those guys. Okay? Now you're like, why on earth would you do that to us, Jay? Because that's how the computer will give you the answer, friends. You're like, well, how the heck am I supposed to figure it? Calm down. It's going to be okay. What I like to do is take the biggest one, so 0.93472998-ish. That's all I worry about, okay? Divide by the smallest one, negative 0.05842, and it's basically 16. Now I probably typed something, and I kind of stopped a little early there. If I typed it in right, I will get 16 almost exactly. If I type in the entire number, I for sure will get that, okay? So that's a 1 on top and a 16 on the bottom. And then if I take 0.9347299834210 divided by negative 0.35052374270, and I'll get that right there, which is, what's the type something goofy? Oh no, that's not goofy at all. Never mind. That's not goofy, friends. That's not goofy. Like, why does it come out 2.66? Hey, check it out. Oops. 2.666. You with me? So you're like, what should I have done instead, Jay? You should have done negative 0.35052374702 divide by the smallest one in that list, which was negative 0.0584. Negative 0.0584-ish. Okay, and you'll get it 6 right on the button. You see that? And if you don't round it off too much, it's actually a really nice deal. But that's how the computer will give those to you. And so without any further ado, allow me to demonstrate. The 2x2s, you're going to do 2x2s by hand. 3x3s, I'm not going to make you do any 3x3s by hand. I just wanted you to see kind of where they come from. The only thing you'll have to do on a 3x3 by hand is that sometimes there are what are called defective eigenvalues on a repeated root. Okay? And so we'll get into that a little bit later on, probably in a different video. I want to get to the general gist of these tonight, how these work. Okay? So the function here we had was negative 2, comma, negative 4, comma, 2, and then semicolon, and then negative 2, 1, 2, oops, that's a 4, stupid, and then semicolon, and then 4, 2, 5. And then at the front of that, what you should have done was you just come in here and go second math matrix 9, and it will list out your eigenvalues for you. And you see 5, negative 5, then 3, then 6 with the order, and it gives them into you from least to greatest. That's how it gives them to you. There's nearly no rhyme or reason other than that. Now come in here and just backspace alpha C, and now you're going to find the eigenvectors. The first one it'll give you, the first column vector, will be the one associated with negative 5. The second one over will be the one associated with 3, and the third one will be the one associated with 6. And there you have it. And you're like, wait, what just happened? Yeah, look at it. Look at it. Oh, it's almost as if Jay knew what he was talking about, except I had a negative sign wrong somewhere. You with me? Or did I have all negatives on mine? I don't know. Whatever. So, again, this is why I don't believe in doing them by hand a ton. Because I waste a bunch of time, and you're like, what did you learn? No, not a lot. So there it is. But again, there's your 0.0584. This is a 1 to 6 relationship between the top one and the middle one. And it's a 1 to 16 relationship with the bottom one. Okay, I had my signs wrong, clearly. If you look at this middle one here, the middle one, for instance, you're like, I don't recognize those relationships. I don't know. Let's see. 0.534522 divided by negative 0.26726, and you'll see that that is basically a 1 to negative 2 relationship. Are you with me? And so, or a negative 1 to 2 relationship. And then if you did the middle one, well, the middle one there would be negative 0.8017837, whatever, divide by negative 0.26726, and you'll see it's a 3 relationship. So I could have gone with negative 1. Remember, the other two are negative is, so it's negative 1. When I divide that out, negative divided by negative is a positive. They had the same sign. And what just happened? Stop it. Stop it. And then, God dang it, I'm having my problems tonight. Number 2. This guy right here is a very legit thing. But notice that this could also have been replaced with this. Okay? Because remember, any constant multiple of this guy will work. Okay? And so, if you think about this, what is the length of this vector? It's the square root of 14, I believe. So if you divide all those by the square root of 14, you would get the same answer as well. Why did the calculator do that? It just makes the numbers smaller, I guess. I guess that's why. No one asked me, and so I don't care. It was only a couple years ago when I finally realized that's what they were doing. Notice that here on this first one, it's a 2 to 1 to negative 1. And that would be the one that would be associated, again, with, they go in order, negative 5, 3, and 6. Okay? All right, let's do one of these, another one that's pretty straightforward, though, start to finish. See if I can unscrew this up. Again, I want to do this in a way that is hopefully helpful and not a giant pain in the tushikins. The idea is not to do a bunch of algebra, so I'm not going to be assigning 3x3s by hand. I do not believe in that. I mean, I think it's important to see 1 or 2 of them, but all you end up doing when you do that is you end up screwing things up. Okay? Come on, Betsy. There it is. So here's a dandy. Oh, it's a beaut. That's my A matrix. Cool. You will, again, on the test, be responsible to be able to do eigenvectors by hand on a 2x2. 3x3, not going to happen. Okay? I'm not going to make you do that. I don't believe in it. This is 21st century. Okay? Oh, you filthy hippie. Forgot a bracket. And now what are you upset about? Filthy hippie. Now what? Oh, I didn't put a comma. Rats! Now I put in 2 commas because I'm an idiot apparently. Hey, I did it right that time. What do you know? -2 for -2. Now, this is saying we have a multiplicity of 2, or a repeated root, if you will, at -2. Now, bear in mind that may or may not cause us an issue here. So check this out. when I go in to do this, again, if I just come in here and go, let's go change this L, which stood for the eigenvalues, to eigenvectors. Here they are. So notice that's going to be a 1, -1, -2 on this guy. On the middle section, it's going to be, notice that they're all negative on the middle one. You see that? Well, if they're all negative, they're all positive. So 1, 1, 2. Because remember, there's absolutely no reason to use negatives because I can multiply through by -1. Any constant multiple of an eigenvector is an eigenvector. And then I get this mess, and you're like, what in Sam Hill is this thing, Jay? I don't recognize it. No, you know I don't either. I'm not going to lie to you. So I'm going to take -0.7575. Oh, I didn't put the point there, did I? 69582 divide by yeah, you're like, oh, that's just awful. It is awful. There's nothing pretty about that one. Okay. I may have to include more numbers here. 2, 4, 5, 6. And so you see you get weird numbers here. And that's not the end of the world, okay? Just be aware of that. Once in a while, you're going to run into some gross ones. I shouldn't say once in a while. Frequently, you're going to run into some gross ones. -6.85, 5.585. Oh, 585. There you go. Is there any reason, Jay, we couldn't have just left them as these disgusting 0.75, 0.64, and that? No, there's no reason you couldn't have done that too. Notice that I left the two negatives here and here. You're welcome to do that. You can put the negative here and make those both positive. Okay, this is not a defective eigenvalue situation. Once in a while, you'll run into two where they can be done different. In a situation like this, where they can be done with two different solutions. Okay, so I want to show you that on this problem here. So I'm going to go ahead and reduce row echelon this guy, or reduce it down. See what I end up with. I'm also going to use the computer for that because, well, I can. Oops, there it is. Come grab it. There you go. If you come back to the front, second matrix, reduce row, right there. And you're like, whoa, oh, what are you doing? Now, that's not what I wanted to do. You notice that? So it's close, but not quite what I wanted to do. What I need to do is I need to go in and I need to put in the values. Remember, we're doing minus lambda, minus lambda, minus lambda. Are you with me? So when I do that, let's look at it and see what happens here. Okay, so I'm going to go in. I'm going to put in -2 first. Are you with me? So I'm going to show you a cute trick that I like to do sometimes. I'm just going to go minus alpha A minus alpha A minus alpha A, and then just inside of here I'm going to go such that A equals, oops, A equals -2. Oh shoot. I get that. So I get A minus B minus plus C. A minus B plus C equals 0. Does that make sense? Ever see that? Okay. So what I need to have is I need to have numbers that work for that. And you're like, well, aren't there a variety of numbers that work for that? Sure. But the ones that the book used, or the one the computer came up with, is 1 minus a minus 1 minus 2. So 1 minus a minus 2 is that. Now you're like, is that the only one? Well, no, of course not. You could also have done, for instance, you could also have done negative 6.585 minus a minus 5.585 plus 1 equals 0. You with me? Jay, that's kind of a dumb one. It is. Wouldn't you have done, if you were doing it, Jay, wouldn't you have done 1 minus 2 plus 1? That's what I would have done. Well, you mean there's a variety. Literally, there's an infinite number of them. Okay. And because this one comes out this way, this is not defective. Oftentimes, not oftentimes, sometimes there are times when it comes out to where there's only one solution that you can get. One solution that's unique. Okay, there are an infinite number of unique solutions, but sometimes you might have come up with 1, 1, 1 or something, and that could have been the entire solution. You're like, well, yeah, but you could have just made it 2, 2, 2. Okay, but that's the same solution. Okay, but doing it my way, which is this guy here, this is completely unique from that guy, which is completely unique from this guy, and in this case, they're not what we call defective. Okay, once in a while we'll run into them. I'll do an example of those later on a different one. When we are in differential equations, we run into those fairly frequently, and we have to worry about those. So you're going to be doing some of those. So that's true. And then we're also going to look at the basis for the eigenspace real quick. And then we're going to call it a day, I think, at that point. I'm going to make a separate video for the specific algebraic functions of a determinant, but how to do them, that's all I need to do to teach eigenvalues. Okay, so once you understand how to do them, and I personally only teach expansion by minors. That's the only way I do it because it's the only way that ever made sense to me. I will endeavor to show you another way, maybe, but I don't really like it. Okay, so here we go. One moment, and we're gonna get ready to go again. Okay, so I'm just gonna run through a couple more examples here, and we'll talk about the eigenspace a little bit. So if you want to find, I'm gonna go ahead and use the same one I've been using here, the last one I just used rather. I believe this is the one I just got done using. And we said his eigenvalues were, where did I write them down somewhere? Didn't I write these down? Oh, fart. Or no, is this a different one? No, wait, I better go to the one I just did. Yeah, it's the same one I just did, you ding dong. Yeah, -2, -2, 4, -2. Okay, that's nice. Now, what I want to do though is this. I want to say, well, let's just take a look at this for a second. So what happens if we were to take this guy and take him, let's do a minus I lambda, or lambda I, whichever you prefer. Okay, and then let's augment it with 0. So what is that going to look like? It's going to look like this, and specifically we're going to put in -2 here. Okay. Yeah, well, yeah. So if I do that, I'm going to get 1 minus 2 is -1. And then I'm going to get this. -5 minus -2 is -3, I believe. And then I'm going to get 6, -6, and then 4 minus -2 is 6. 1 minus -2, this should have been 3, I guess. Huh? Is that right? Yeah, I believe that's right. Okay, so what's going to happen when I do this? Well, what's going to happen, obviously, I'm going to get 2R1 plus R2. Well, I'm going to get 2R1 plus R3, minus R3, rather. and I'm going to get R1 minus R2. And I'm going to end up with so if you will, the nullity here is 2, right? It's a dimension of 2, right? You have 2 free variables, if you will. So we're going to look at the eigenspace, and so we're going to have 2 vectors, if you will, that span this because there are 2 free variables. Okay, that's what we're looking for here. Okay, in this situation. Okay, in the case of if there's only one variable, if there's only one empty row down here, then you'd be looking for one vector that would span the eigenspace. Okay, that forms the basis for that null space. So how's that going to work? Well, I don't know. Check this out. What I would also do then at this point is divide by 3. Oops. Okay. And now that I've done that, you're like, well, what does that buy me? Okay, well, actually, quite a bit, actually, I think you'll find. So what you're going to see is that, of course, what does that mean? It means A minus B plus C is equal to 0, as we mentioned previously. Okay. But since we have this scenario here where these guys are free variables, we're going to let, if you will, and we're going to, the way your book uses this, it uses this as x1, this is x2, and x3. So I would always talk about this in my differential equations class. I like to view them this way. But this book does them this way, and it's fine. It's just a different way of going about it. It's different nomenclature, same principle. x1, x2, and x3. Okay? So I will from time to time, put in A, B's, and C's because that's what I'm most comfortable with. I always have been. Learned it that way myself. So here it is, whatever. So what we're saying is this. We're going to let x2, we're going to let it equal some value. We're going to call it s. Okay? Again, this is your book's terminology. And we're going to let x3, because it's also free, we're going to let it equal t. Okay? And so when you look at this, what we're saying then is this. You're going to say x1 minus s plus t has to equal 0. In other words, x1 has to equal s minus t. That makes sense? Okay. You're like, what does that do for me, Jake? Just bear with me. I'll get you there. I promise. Okay. And so what we're going to see is this. We're going to take a vector. We need a vector that looks like this, and another vector that looks like this. Okay, and so x1 is this top row, if you will. x1 is whatever's in this top row here, plus whatever's in this top row over here, right? Well, we said x1 has to equal s minus t. Well, that means this has to be a positive 1, and this has to be a negative 1. Fair enough, I guess. We let x2 equal s. Well, x2 would be this middle row plus this middle row. Well, there's no t, so 0 here and a what here? A 1, of course. And then x3, of course, we need to have it to be a positive t rather, so a 1 and a 0. So these two vectors span the eigenspace. In other words, they form a basis for the eigenspace. That's how that goes. Okay. So in other words, they will generate the eigenspace. That's the game there. Okay, we'll look a little bit more at what the how comes that is, and what does that tell us later on. Now, what happens if you did the same thing with fiddle faddle? Same problem, but let's use our 4 instead, shall we? So if I did the 4 instead, that's going to give me 1 minus 4 is negative 3. I can't do this in my head. Negative 3, negative 3, 3. Oh, they're both negatives. And then the middle row, if you do minus 4, it's going to be 3. It's going to be negative 9, and then negative 3. Or positive 3, you dope. And then it's going to be 6, negative 6, and 0. Okay? It's pretty clear from this problem going in, it looks like we're probably not going to have rows that are linear combinations where we're going to end up with 2 rows of zeros. Could be wrong. Don't think so. Let's go see. Okay? So let's do, right off the bat, let's do a little R1 plus R2 and a little 2R1 plus R3. Yeah, Jay, couldn't I just do reduce row? Yes, you could, but I don't. I'm going to go ahead and show it by hand. Thank you very much. I earned my keep here at 0, negative 12, and 6, and 0. And then you're going to get 6 minus 6 is 0. Negative 6 plus negative 6 is negative 12. And you're going to get 6, and you're going to get 0. Excellent. You're like, wait, what happened here? Oh, wait, hold up. Now, hold up now. You're like, well, what just happened here, Jay? Well, that's good. Now, wait. These two rows are the same, but what is that going to give me then? Okay, it's going to give me this, 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 and this. And then it's going to give me this, 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 and this. Notice how in this situation, okay, in this situation here, what do you have? Well, you have one null row or one empty row. Does that make sense? So you have x3. We're just going to let x3 equal t this time. Okay, we're just going to let it equal t this time, and just let it do its little thing, hang out, see what happens there. Okay, now when you do this, obviously that top row could be written as 1, 1, negative 1, or you could leave it the way it is. It doesn't matter. Whether you like this, or like this, it doesn't matter. But let's just see what happens here. What are we saying? We're saying that x1 plus x2 minus x3 is equal to 0. Or, if you prefer, and I do, x1 is equal to negative x2 plus x3. Okay? And then, in the middle row, you're going to have x2, 2x2 rather, is equal to an x3. Okay? Well, wait a minute now. That's interesting because when I do this problem, that means to me anyways, that I see here, I see that if x3 is t, then I see that 2x2 is equal to t. Well, interesting. So then x2 is equal to t over 2, Jay. Is that right? That's right. Good job. Good job. And then wait, can you then back substitute up one more? Sure you can. So then you're going to get negative t over 2 plus t, which is going to be equal to 1/2, or t over 2 rather. You see this? So when you see this problem, what I see is I see that t times 1/2, 1/2, and t, and 1. Yeah, that's right. Okay? You're like, I don't like that. I don't like fractions, Jay. Okay, good. Remember, any constant multiple of this makes the job work, so it's times by 2. 1, 1, 2. That right there, this guy here spans the would span the eigenspace for that guy, right? And so that's just what you're going to be asked to be found out there. It's kind of fun, almost, and there you go. So, by the way, note that we only had, when you used, this was for lambda equals 4, correct? When I did for lambda equals 4 was just it just had a multiplicity of 1. In other words, it was not a repeated root. Multiplicity of 1. And you're like, oh yeah, right. Well, so in other words, what did you find? Well, that is, you only had one free variable, and you could do it with one vector. But up here, negative 2 had a multiplicity of 2, and so as a result, what did you need? You needed 2 vectors to span the eigenspace, or to form the basis for the eigenspace. Okay. Now, what does that have to do? All right. So I wanted to say something here. Some people will sometimes look at you and go, "What do you mean, Jay? What are you saying by this, Jay?" Well, remember, I've said to you a bunch of times that any constant, any integer value, any constant times the eigenvector is another eigenvector. Yes. That's literally what you just found out here. This guy right here, because you can multiply by any value, t. Doesn't matter, which I've said is k, right? Because you can multiply any value. What it's saying is that that will span, it will create every single possible eigenvector for lambda equals 4. You're like, wait, look at this picture here, Jay. Isn't this middle one right there, 4.4, negative 0.4, negative 0.4, negative 0.8, isn't that the same as this? Well, by God, it is. If you did negative 0.40, whatever it was, I forget, times 112, you will get negative 0.408, negative 0.408, negative 0.816, or whatever, which is exactly the same thing. Wait a minute. Are you saying that up here, when we got these guys, that S times this fella plus T times this dude will create every single possible combination of eigenvectors for -2 and -2? That's literally what I'm saying. Wait, no way, Jay. No way. Let S equal 2. Let T equal 1. I don't know what'll happen. I just can't. I don't know. That's 2 minus 1 is 1. 2 minus 0 was 2. And then you're going to get 1. No way. But, Jay, that's the one you said to use. I did. I know I did. Yeah, that's right. I believe I said that's the one I said you could use. Because if you recall, right here, I said A minus B plus C. That's what I said I would use, 1, 2, 1. That's just me personally. Okay. Now, wait a minute. What if you hypothetically let S equal, I have to peek, don't tell me yet. Don't tell me, I forgot. Look it up. Hypothetically, what if you let S equal 0.757 and you let T equal 0.642? What would happen there, I wonder? And so off you go to the races, and it's very interesting if you play these games out. You're like, well, that's cool, Jay. But what if, actually, that's not quite how I want to do it. What if I did this one? What if I did this? Negative 0.75. No, 0.65. Negative 0.65. 6425, I'm sorry, 6425. And what if I let T equal, again, this is totally hypothetical, 0.115. What do you get? Well, you get negative 0.642 minus 0.115 is equal to negative 0.757 or whatever it was. Then you're going to get negative 0.642, whatever it was, and then you're going to get 11. Like so. Boom! And that is another example. Again, they will always be in this format. This is why, and I cannot stress this enough, that this is why that there is an infinite number of them. It's because this guy right here spans it. And therefore, you can multiply by anything you want to right there. They're just linear combinations. Well, that one's just multiplied by a constant. These guys here are linear combinations. Okay? And so any of them would work. Wait, are you saying that you could let S equal 3 and T equal 4? Literally, that's what I'm saying. That would be -1, that would be 3, and that would be 4. Done. Boom. Bob's your uncle. Okay? Always will work that way. Always, 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 always. Take it to the freaking bank. Okay? Sorry I had to say that for last. It's kind of a big deal. Okay? So I will be making a video, follow up another video tonight. It will have more about determinants, some of the algebra behind them, and we'll kind of see where we go from there. Come on, open up. Stop.